Can you go to the make refer page and click on presentations to see if it takes you to the right page? Miami.makerefer.com. Huh? Presentations.
Wow.
Hello, everybody. Welcome to the Year 2, Phase 1 presentations for the Growing Beyond Earth. Oh, sorry. Wow, I did not let anybody in. Let me let everyone in first. There we go. All of our teams will be joining in now. Awesome. Okay. So, hello, everybody. Welcome to the Growing Beyond Earth Year 2 Phase 1 presentations. We're really excited to see each team show what they've been working on for the last couple of months. It's been an intensive process for everyone. And we have our panel of judges today that will be hearing each of the presentations and weighing in and giving some feedback on what you're presenting. So we have Ralph Fritsche, the Senior Project Manager at Kennedy Space Center, focused on food production technologies. We have Dr. Carl Lewis, botanist and director at Fairchild Botanical Garden. And Mario Cruz, technologist and patent holding inventor of various software and hardware innovations. And they'll all be weighing in on different aspects of your projects today. So Dr. Carl Lewis, if you'd like to lead with a few words.
Sure. Just want to say hi and thanks and welcome to everybody. I'm the director of Fairchild Tropical Botanic Garden, and we have this beautiful botanical garden here in Miami. It's a spectacular day to be here. And we've been involved in this program now for several years. I'm the principal investigator on the grant that NASA is funding to establish the makerspace here at Fairchild Garden. And actually, that's where Tom and Mario are right now in our innovation studio. And the NASA grant is also funding this nationwide maker challenge that you're all involved in. And the way this works is that we have an idea and write a grant proposal, and then it takes a few years for that to come to fruition. And it's just so thrilling to now see that all these great ideas are coming together out of what started as a simple concept. And what really was inspired by conversations with Ralph Fritsche and things that Ralph taught us about the challenges associated with growing plants in space. And we tried to distill these challenges down into some simple concepts. And that's what we put into the proposal. And then we leave it to people like Tom to translate that into a challenge that you all can actually try to achieve. And then we leave it to you to be creative to figure out how to meet those challenges. But here we are in year 2. And so it's great to see some of you that participated in the year 1 challenge carrying it all forward to year 2. And the basic idea was in year 1, think about how to make the best use of the limited 3-dimensional growing volume on spacecraft. How do you squeeze the most plant production out of that limited space? And we got some great ideas last year and great concepts that actually work great. And then this year, the idea was to automate things and figure out, can we have a garden on spacecraft that can actually take care of the plants? And this is at a time when there are all kinds of different products coming on the market that are supposed to automate gardening and take care of the plants. And that's fine as a hobby, and it's fine if you want a thing to work with and look at, but is it fine if your life depends on it? Is it really reliable? And so we thought of this year as sort of almost like the DARPA Urban Challenge of plant growing, of gardening. Can you set it and forget it and come back and have your plants and harvest? And then this is all building in complexity for next year to be the challenge where we have robotic planting and harvesting of crops. So this is intentional that it's getting more and more complex. And so we're really excited now to see what you're all going to present today. So I'm just going to be happy to watch all this. And again, thank you for all of your very, very hard work.
Thanks, Carl. And Ralph, if you'd like to weigh in a little bit about how NASA is using all of these open source projects to further develop the initiatives at Kennedy Space Center.
Sure. So I think it's important to realize that the number of people who are working in this space within the space agency and NASA is relatively small and few. And not only are we trying to look ahead towards future applications of plant growth to support the food system of Cruz on the moon and Mars, we're working missions into the International Space Station right now, where we're trying to conduct that fundamental research. How do plants behave in microgravity? How are they going to behave when I get beyond low Earth orbit in the radiation environment of deep space? And we simply don't have the manpower to, or the people to do everything that's required to be able to answer all these questions. So really, depending on the folks like you and how the support we get from Fairchild, taking some of these notions that we just don't have the ability to focus on, doing two things: coming up with ideas that we can actually build upon in the near term, as well as instilling upon all the young people out there the desire to continue in this advancement, because in the next 10 or 15 years, you're going to be the folks doing it. When we talk about crop systems that are going to make their way to Mars, for example, right now the timeline for the first crewed mission to Mars is 2039. So I think I'll be retired by then. And so hopefully some of you folks will be the ones taking over. And I think having a ground level knowledge and understanding of the challenges at an early age is really beneficial. I didn't get involved with plants at all till maybe 6 years ago. So for me, it's been a lot of catch up and learning. And just having people who are taking over is a huge thing for us. And I really also don't want to minimize the solutions that I expect to hear over this time today. I really expect to hear of innovative ideas that we haven't had the chance to consider yet. We've already seen that in a couple of applications that have made it to space for testing. So I'm really encouraged to support opportunities like this for you guys. I think it's a great thing. I don't minimize the products that you're coming with at all, and I wouldn't want you to either. So today you might get some criticism and feedback, but that might be brutally frank, but that's because we really value the work you're doing. And I want to make sure that you're on the right path wherever I can and tell you about the nature of these challenges. Space isn't easy. Growing plants in space isn't easy. And ultimately, what we're doing is we're ensuring the health and performance of the crew on these missions that are long duration missions far away from Earth. And we're also laying the foundation for sustainability and Earth independence, which is what it's going to take if we're going to actually be successful with the future of space exploration over the next 50 to 100 years.
Thanks, Ralph. All right, and we have Mario Cruz. He's taken a number of products, software and hardware products to market. So he'll be weighing in on all the technical details of your project. So Mario, if you want to talk a little bit about that, what you're looking for today.
Yeah, just like Carl and Ralph said, I'm very excited to be working on this. Again, working with Fairchild and NASA, we were able to help get this lab built here inside of a garden. And again, we're testing and hopefully building the future folks that can do this in the future, right? Like Ralph said, we're trying to create the roles and the products for who does this in the future when we're getting there, and this becomes the norm, right? When we're flying across the ocean, those are game changing. Now we fly across the world, and that's game changing. Flying to the moon and Mars will be pretty much a daily activity probably in the next 30 years. So we're trying to get things done and how we do that at scale.
Thanks, Mario. So we have a selection of the projects represented today. These are folks who have really gone above and beyond with their projects. And it's broken down into high school categories, collegiate categories, and professional categories. So we're going to start with the high school teams. And let me see here, if we can get the Cami, computerized agriculture monitoring interface team, to unmute themselves, and I'll spotlight you, and we'll bring the judges to the background to hear your presentation.
Great. So good afternoon, everybody. My name is Chris Rogini, and I am the teacher who was fortunate enough to work with Noah Berlin and Nora Kay, who are 8th graders at West Hollow Middle School in Long Island, New York. We are going to present our version of an automated growing system. And I will start by introducing the project, and then I'll give the spotlight over to Noah's to kind of follow up with some of their experiences with it. We are really honored to be a part of it, and I'm sure a bit nervous as well. So boys. It's going to be okay. I promise. All right. So let's start off. I guess I'll share my screen and we'll give you a little intro and then I'll turn it over to Noah and Noah. Okay, so we named her Cami. It's our computerized agriculture monitoring interface. We focused on the GBE unit that we were sent as part of the Fairchild program. And the boys have really knocked me out with the way that they've picked up everything from soldering to coding to electronics over the 2 or so years we've been working on it. So interestingly, this challenge came along and it was kind of awesome because we've already been doing these things for a couple of years as part of our time together in our classroom. So, watching them go through the prototype phase and then actually assembling it was pretty neat to watch. So sum total, our system has about 18 sensors, 6 actuators, there's a camera inside, and over 20 variables can be monitored at any given time. And the current input-output systems that we've designed over the course of several years, and there's been many kids who've contributed to this along the way. The NOAAs have really focused on soil moisture and pH, but we are able to control soil temperature by way of a heat mat, our air temperature and humidity by way of fan speeds, soil moisture with water pumps. We adjust the pH of that water using peristaltic dosing pumps. And then we are also able to monitor through like a closed loop that the lights are on or off with a light intensity meter that switches over to an IR floodlight so we can view our plants when it is dark. So we focused on the ISS grow chamber to begin, and we wanted to also understand the scalability of it to have the whole farm kind of taken care of. So we are also thinking about once we get off the spaceship, once we do colonize Mars and we're there on a regular basis, could we expand what we've done in our little box to an entire greenhouse, perhaps? So my high school students have focused on Fusion 360. They have rendered different types of project boxes, which we typically 3D print or laser cut on our Glowforge. And then the NOAAs have really kind of like infused their electronics and their code within these boxes and then mounted them within the systems. And one thing that's really neat is the boys were able to put together using Adafruit IO, an online dashboard of widgets that are making our data accessible anytime, anywhere, as long as you are connected to the internet. So we can get both inside and outside of the grow chamber a look to see any of the environmental variables that we are currently monitoring. And additionally, they have created systems that are both manual and automatic. So while we are in the lab, we can manually fine-tune set points and administer pH dosing solutions or water. But when we have long-term care needs, such as, leaving our excursion and going on exploration missions, we can hand that off to Cami, and she can go ahead and monitor those variables for us based on set points that are predetermined, and allows for us to take a look inside the chamber to monitor general plant health from afar. We have hopes of adding more capabilities to those cameras. Long term, we would love for the system to be able to measure our plants for us, to make color determinations on plant health, as well as be able to measure the mass of the vegetation within those units, by way of some digital scales that we'd like to put underneath the plants themselves. So it's a little bit of an overview of, the system itself. Noah and Noah, you guys want to talk a little bit about some of the systems that you've worked on?
Yeah, sure. So my biggest part that I've been working on for the longest within the project is pH automation, where he mentioned earlier, we use peristaltic pumps to adjust the pH, and we can do that both automatically and just let our systems run, or do it manually and pump it whenever we want through our Adafruit online dashboard. And that same concept works throughout all the different variables in the growing chamber.
I was working on a lot of the putting all our data that we have received online through Adafruit IO. And very interesting how it shows everything and anything that you want from our farm online, on the ground, anywhere. You could turn it to auto mode and manual mode, so to get exact readings and doses that you need on manual. But again, if you can't be there, you can go to auto, like for our missions, like Mr. Rogini said before.
So one of the most challenging parts with this is that when our pH sensors take a reading, it's not just like pH level like 5. It's different, and so we need to use math within our code to convert that into an actual real world number. And that's been a challenging step so far.
Yeah, like when we forget a decimal point, Noah, right? And the whole thing falls apart because we needed a float.
We've spent days trying to make adjustments when we just needed to add a 0.0.
I've been working on I've been working on putting a little device or underneath a plant's leaf to calculate the humidity in the room and the temperature, so we could change it. The plant is telling us what we need our temperature may be, not us. The plant is going to tell us what we need to be, and we will change it according to what it says.
So you were kind of taking stuff from your earth science class, right, Noah? With
Transpiration, yeah.
So since we got the pH automation system to work, my next step so far has been to add it so we can have multiple sensors and pumps working together simultaneously. And since in our classroom we have 3 growing chambers, my goal so far has been to apply it to 3 different systems. And the hard part with that is that we need to adjust each system individually, because not everything's going to be the same with the different types of plants we're growing. And that's been my work so far.
We plan on learning, me and Noah both plan on expanding our skills in Fusion 360 and just CAD all together, so we could really expand this project that we just don't want to be a small box. We want it to be huge, and just so if we get to Mars, this is how life could be. We can get food and vegetation.
Yeah, I think expanding the system within CAD is very important, so that we have a big housing chamber that makes sense and is easy to follow for whoever may be on Mars. And our skills within CAD has been a priority lately as well.
Thanks, guys.
Awesome. So do we have any questions from the judges?
What sensors are you using? I saw some sensors in some of the pictures, but can you just give me a general description of all the sensors you're using, and how you have them wired to your box?
So
Yeah,
you want to talk about your sensors that you've been focusing on specifically, and then I'll add to the ones that the other kids have worked on.
All right. So to start, we've been using pH sensors that go into the soil, and also the sensors that Noah talked about earlier that go into the stomata of the leaf to get the plant's humidity.
Also been working with moisture sensors. I've been working with that more than he has. So we could add the water when necessary to the soil and make sure that it's not too wet or too dry, because then plants can't survive.
And how often are you checking that? Like every 10 minutes, every 15 minutes, every half hour? What's the cycle on those sensors? You have both, Noah's?
It's usually,
No, go ahead.
all right. It's usually, I think we have it set in every 10 minutes in our code as of now, because you don't want it making readings every second otherwise, because it needs time for the solution to actually have an impact before we make another reading. So I think we have it around 10 minutes right now.
It could always change though, depending on the needs and necessities of a plant.
And have you guys monitored those over a weekend or a long holiday to see everything is working?
So
yeah, like when we went on vacation over December break and February break, we have had those been monitored.
That's been the goal with our Adafruit dashboard, to monitor the different variables when we're not in the classroom.
Thank you.
Those are I2C sensors from Atlas Scientific, the pH sensors that we are currently using.
Okay. And then are they going to a Raspberry Pi, or what's the host for those? Or are they just going to something else?
Raspberry.
We go to Raspberry Pis. I believe we're using Pi 4s, right?
Okay.
So it just goes to our Raspberry. We've been using code within Donnie and Python to our Raspberry Pis, and all the data goes there.
Awesome.
So I have a quick question for Noah K. You mentioned the moisture sensors determining whether conditions are too wet or too dry. And you also mentioned how you'll have to tune things for the needs and necessities of each of the different kinds of plants that you're growing. How do you know what those needs and necessities are, and how do you know what's too wet and what's too dry for each of the plants you're growing?
Well, it's going to be a trial and error run. So you get the plant you have, and let's take moisture, for example, here in the soil. If you think you cover the base that you think could be correct, and if it's wrong, then you just have to keep on trying until you find what will be correct, and then just target it from there. And with our electronics and Adafruit, it could keep at the same point with no error. It's be you want it at 5.5 or whatever you want it at, it would be there.
Okay, so you're looking for the plants to give you a signal that they're growing well or not.
Yeah.
All right, I've got a question and a couple of comments. First question, when it comes to the pH sensors, are you tagging them one per plant, so to speak, or how are you determining how many you're using and how you're placing them?
So we have one per plant and 2 pumps per plant, one to adjust it to make it lower and one to make the level higher, based on the solution and based on our data.
And I don't know if I saw it on your illustration, but are you using a growth medium, a soil medium, and individualized pots or containers for each plant, or is it in a community growth space?
It's different. It's a different medium for each plant as of now, but that can always change if we'd like. And we've been experimenting with different mediums so far.
Okay, so I guess on the comment side, I'd like to say that I'm amazed you guys are really capturing a lot of the key issues that we would deal with, especially in a microgravity system in low Earth orbit where I don't have to worry about the radiation. And you've got some of the basic parameters down there. You're working at really fundamentally extremely impressive. I think, you know, one of the things I was just going to comment on, this isn't a critique at all. This is just an idea about when you talk about manual versus automated, that's really an important concept. And I can tell you a little bit about how we're envisioning it. Automated requirements come into play and are going to be probably very crucial when I start talking about surface operations, where the crew is going to be really busy with conducting EVAs and research on the surface of the moon or on the surface of Mars. They're not going to have time to tend the plants. But when I start talking about these long duration missions to get to Mars, things that might take, you know, almost a year to get there, it's very likely that we are going to be looking for things to have the astronauts do, simply because for a large period of that time, we're going to be too far away from Earth to conduct meaningful research and too far away from Mars, again, to conduct meaningful research. So trying to keep the crew occupied with meaningful work is going to be an important thing. And you know, one of the things I just want to keep in your mind, what we look for growing plants really is a supplemental source of nutrition on these missions. There's also this psychological benefit of having living things in the environment with you. So don't forget that as you design hardware, make sure that the crew has the ability to see what you're growing. We may not want to have them have to look at the growth lights all the time, but the ability to be able to see that is very important. But I'm really impressed with everything I've heard in this project so far. Thank you.
Thanks so much.
Ditto that, Ralph.
Awesome. Well, thank you so much, Team Cami. We're going to move on to the next team, Gaia, from the STEAM Club at Palmer Trinity. Give me a chance to just bring them on the screen. All right, so Ben, are any of your other teammates on? Or okay, so you'll be representing Gaia.
We're all taking the ACT today, so.
Well, thank you for taking the time out to to present your project. You have the floor.
Okay, so my name is Ben Arnold. I'm the president of the STEAM team at Palmer Trinity School in Miami, and our box is name's Gaia. So here are just some of our members of the team, here, the main four, and Nick is our secretary. He does a lot of the organization. Jack is the historian / webmaster, and he's the programming team lead. So he did a lot of the programming. And Chris also does a lot of the programming, and he did the website development. And over spring break, he helped build the box. So the next few slides are just going to be the sketches and diagrams of our box, just the isometric views. Okay, so what we are doing is we're using an aeroponic system to grow the plants, because aeroponics, after some research, we learned that it allows the plants to grow much faster because you're directly giving smaller particles of water, so the plants can uptake it much easierly. We're using something called a ultrasonic humidifier chip, and I don't know if you can see my mouse, but on the left you can see the little chip, and that vibrates at an ultrasonic frequency to break up the water so it creates fog. So this whole entire tube will be filled with fog, and then the plants can grow out of it. And then this pump is transferring the water in this 3D printed reservoir in the back to the basin that the ultrasonic humidifier is in. And one of the difficulties we had was we don't know if this will work in microgravity, because the last time aeroponics was tested was in, I think, the 90s. They did a small little research thing on the International Space Station. So we need to figure out how can we make sure that it would hopefully work in microgravity. And we have to learn a little bit more about fluid dynamics to see how we can maybe design the walls of this grow tube to facilitate capillary action to help push the water down back into the basin. So we want to do a little bit more research on that before we fully commit to this aeroponic system. And we believe aeroponics is going to, of course, use a lot less water, which is good because then the astronauts won't need to fill it up as much. So we also are growing everything out of this circular growth tube configuration because this allows us to get the most plants. And right now we are set up to grow 50 plants each month. And we're using an Arduino to help detect the pH and the CO2 level. And it also allows us to turn our growth tube so that if there's an issue, you can always, reach the other plants. And it also controls the lighting and humidity and temperature. So the technologies we used in this design, we designed the whole box in Fusion 360. And actually, a lot of these parts are 3D printed. So the whole entire growth tube and the basin at the bottom is 3D printed, along with the whole entire reservoir. And so we used a Ultimaker 5, and one of the issues we had was we couldn't print out a whole entire 50-centimeter growth tube. So we printed it in sections, and I actually used an old soldering iron that I had to fabricate and melt the plastic together so I can create much larger parts from separate 3D printed parts. And we programmed all of our code using the Arduino IDE and uploaded it to the Arduino. And we're currently still debugging the code because not everything works, but one of our team members, Chris, was just working on the code yesterday. So I'm not going to read the list of materials we used in the box. We used a lot, and from winning the project last year, we actually got a lot of our stuff all out of fruit from our reward money. And I know it seems really messy with all the wires because we haven't fully connected everything yet. This is just more materials we use. This is me working up late in my house trying to figure out how to run all these lights simultaneously, because with the Arduino it's very difficult to programming it to run multiple things at the same time because of how the coding works. And I think that we should end up using a more capable system like a Raspberry Pi in the future. This is some renderings of our box and the actual real box on the top right. And if you look on the top on the left, you can see the motor that will be used to turn the whole entire growth tube. And this middle one is the rendering, of course. And this is the reservoir where the main reservoir, and then the reservoir where the humidifier will sit in. So any questions?
Yeah, why does the growth tube rotate?
Well, so we're thinking ahead for the future, and we do have an idea to harvest the lettuce without using a robotic arm. But if we're growing more complicated plants, we can use a robotic arm and just one, similar to I don't know if you've seen the Da Vinci robots that are the medical robots, but if we figure out how to do machine learning, which one of our team members is going to focus on all summer, to try to figure out how to individually pick, like if we're growing beans or peppers, so that it can, go in there and pick these more complicated plants. So it's so that we can only have one arm and then rotate the whole entire growth tube around to that one arm. And it's much more easier to do that single directional movement than a very complicated movement of the robotic arm.
Well, that's a great answer. I wasn't anticipating that being the answer. That's great. Thank you.
We like to focus on simplicity because it's first more reliable. And I actually believe simplicity is harder to do than complexity, because as humans, I feel like we just like to make things more complex than they really need to be. So we're trying to think of how we can make this box as simple as possible.
Sounds like you're working your way towards year 3 challenge as well. Awesome. Do we have any other questions from the judges?
Yeah, I got it. Well, a couple of comments, maybe a question or two. First off, you talked about your system being an aeroponics system. I just wanted to let you know that later this year, the Sierra Nevada Corporation will be flying a payload to the International Space Station called X-Roots. And the purpose of that payload is to really understand aeroponic systems, watering systems for plants and microgravity. So if you keep in touch with any of the NASA online resources, if you see anything about X-Roots, that would probably inform you of how their results are. I don't know when their operations are set for, but I know the launch is set for this summer. Then the other thing I can tell you, you talked in there also about capillary action. And interestingly, just 2 weeks ago, one of the researchers who we partner with, who's from Portland State University, is a big fluid physicist, and he is very excited about the potential for capillary action and how could we water plants in space, in microgravity, without any medium, simply by using capillary forces. In other words, coming up with a omni-gravity water delivery system, something that would work on the Earth as well as in microgravity or in the partial gravity of the Moon or Mars. So there's more research being done on that as well. The initial results that he experienced over the past few weeks have been fairly encouraging. Then I guess the one thing that would be a question for you or a comment is if you're going to be talking about growing larger plants that are branching plants at all, when I see that vertical tower, it might be somewhat of a challenge to not have the plants growing down with gravity on top of each other. I wonder if taking that and turning it 90 degrees might be a better option. But again, I don't know. I think you might want to just, if you have difficulty, with it in that axis, just turn it 90 degrees and see if how things would work in that regard. I do applaud you, though, definitely for looking ahead to the next phase of the challenge. I think that's important. If you only focused on this aspect of it, you might be ill-prepared to move in and to the next phase of the challenge. It might be even more difficult for you. So kudos for that.
So for some of the larger plants, I think like beans and peppers. I've actually been growing beans in my own garden and have determined a couple varieties that are pretty productive and a decent size that will actually fit in this box. We think that it will be good to maybe make it a little bit more modular to grow the beans from the bottom part, still using the same idea with the aeroponics, but that will allow for there to be a little bit more room, we think, for some of these larger plants.
Hey, go for it, and we're really excited to see how what your results are.
And just to add on to Ralph's comments, I think, yeah, everything that Ralph said, and then I think if you can look at phase 3 and things you're doing now, and especially the power draw on the lights, you should look at a Raspberry Pi and something that has IC squared on it, so that you can have separate power from the power on the compute side, and allow you to do so. And if you're going to do machine learning, like you're saying, with any visual or camera, that's the way to go anyway. Yeah. So you should look at upgrading that as soon as possible. If you're having problems, just forgo those problems and just make a switch now and continue on.
Right now, our lights draw a lot of power, and I think we want to see if we can use fiber optics so that we think that maybe it will be less draining on the amount of wattage that the box takes, but we haven't looked too far into that yet.
Yeah, because one of the things, just piggybacking on that, when I look at the actual operational setup you have there, it looks like if you're generating a significant amount of heat with those LEDs, you're going to have to figure out how to use fans in there to cool the plants and get that air moving around. Otherwise, they could just bake from that.
Yeah.
Great. Awesome. Well, thank you so much, Ben. That's an incredible project and a nice continuation from your development from last year.
Thank you.
All right. So next up, we have the Sequoia School.
Yeah.
Alex Foreman, let me bring you up to the panel.
Awesome. Thank you.
There you are. Okay, so you have the floor.
Awesome, thank you. Yeah, I'm really excited to show this. I didn't make a slideshow, but I guess I'll kind of just walk through the design I've made. This is kind of a continuation of my submission from last year, with a few changes to hopefully be more autonomous. So the frame is just made out of 20 millimeter aluminum extrusion, as it's pretty rigid, accessible and easy to kind of snap together, and then each corner is reinforced with these 3D printed plates, and that also allows these grow beds, as there's 8 in total, to hold on to the sides, or sorry, the corners. And as you can see, the grow beds essentially are these 3D printed holders or containers that have a little like hanging part on the bottom that can slot into this little slot here to hang, as well as kind of act as a slider. And you can see that down here, how these beds can slide in and out for easy access if someone wanted to harvest them or inspect them or whatever. And within these, there are these green squares, which represent the plant pouches. That's what are currently used on the International Space Station, as far as I could tell. Or essentially they're pouches that contain soil as well as the plant, and then they're watered. I wasn't too sure how, or the specificities of the connectors on the plant pouches aboard the ISS. So I designed what I kind of refer to as water needles. I can't really come up with a better term. That essentially were these 3D printed pieces right here that stick into the plant pouches, and then be connected to a central line of irrigation tubing. And then this irrigation tubing would go into the actual little plant tray, and then have a entry point here where we could have a quick connect for main irrigation line, or sorry, not main irrigation line, different irrigation lines. And that again allows an astronaut to take out these trays and study whatever plants or to harvest them. And then all that water is pumped by this central water pump. That's kind of just a standard piston driven by electric linear actuator. I'm not 100% sure if this is correct, but last year, my oldest mission used peristaltic pumps, and a few people reached out to me to let me know that they didn't think that would actually work in zero gravity, which I guess sort of makes sense. So this year I changed it to kind of a central piston-driven pump, which I think probably would work in zero gravity, but I'm still not 100% sure. It should work on Earth, as far as I know. And then we have one intake set of fans with a filter, and then a little outtake fan with a filter before it. Since this would kind of be an all self-contained unit, if one of the plant pouches broke and soil was to come out in microgravity or like in space and was floating everywhere, we obviously wouldn't want it to just be sucked out by fans that kind of blown all over the International Space Station. That'd be pretty disastrous. So there's a filter beforehand to prevent any debris from flying out. And then for kind of the light source, and kind of, in my opinion, the most interesting part is what I kind of refer to as the observation arm. And it's the center pole that is mounted to the back of the frame that has currently 7 strips of UV lights, each corresponding to one of these grow beds to emit light so the plants can grow. And the reason there's only 7 and not 8 is on the top we have a timing belt that in the back is driven, you can slightly see it here, by this stepper motor and a small pulley. And what this, the function of this essentially is to control this main carriage assembly that can move back and forth. And then within this, there's an outer ring on the carriage with a, I'm forgetting the name of it now, but the type of gear that is, inner. And then that's controlled by a small N20 size motor here, and then supported by a bearing here. And what that allows is for this whole outer ring to rotate fully around the center shaft. And then on that, I have a camera, an ultrasonic sensor, but theoretically you can have any sensor you really wanted to. And the reason for all this is that way we can capture pretty much photos of every plant from multiple angles. And this year I took a machine learning class at my school and learned a lot about building image classifiers, specifically in Python, which is also kind of why I chose to all this be based on Raspberry Pi. So theoretically, if we wanted to, we could train image classifier on whatever plants we were growing for overwater plants, underwater plants, plants that got too much sunlight, too little sunlight. And then every day or every like 8 hours or so, this carriage could rotate throughout the whole little environment and take photos of every plant and measurements, and then put that into the classifier and see if the classifier thinks it's overwatered or underwatered. And then with that, it could then deliver more or less water or more or less light, essentially. So it could be fully autonomous in terms of all the variables in this environment to grow the most optimal plants. And also it being fully rotatable allows us to kind of get rid of outliers and possible data. If we just had a camera on every side of this octagon, there could be things such as light glare that would make a possible image classifier think that there was like a white speckle on that plant, when in reality it's just light glare. But if you're able to take photos from multiple angles, you kind of get rid of that chance of anomalies. So then this carriage, the majority of the time would just be resting in kind of a home position back right at where the stepper motor is. So then the light would be coming out of the center pillar. And I didn't put it in my CAD design, but I was thinking that since light strips are actually flexible, what you could do is lay UV lights on the timing belt. And then when the main carriage kind of extended, since those are flexible, they just flex with the timing belt. But I didn't design it, and that would kind of need some testing, as I don't really know how fragile LED lights are, and you might end up kind of cracking them if you keep bending them over that pulley. But yeah, that's my design. Thank you.
Have you looked at?
So Alex, did you come up with this on your own, or are you part of a team? Since I've only heard.
No, I'm the only one on the team. Yeah.
All right. So let me give you some feedback. From an engineering perspective and how you've designed and thought of the engineering aspects and principles behind it, it's very impressive. It's definitely the kind of thing that I could see as a viable concept that some of our engineers would have come up with for the International Space Station. There are some challenges with that we all face when we start selecting how we're going to design a system like this. And sometimes it takes a lot of interplay with the biology side to be able to sort those things out. One of the challenges we've talked about by having a central lighting core like you've done is that as the plants start to grow, now when their canopies would require more space, they're actually being constricted by the geometry of the setup that you've designed. So that's a challenge when you think of how much space you have in there from where the plant where the substrate is in the housings where the plants grow from to where the light source is, you don't have that much height in there. So that's going to limit the type of crops. That's not a problem as long as you recognize that going in. Then you also have mechanization there that might require, a lot of maintenance over time. So that's something we try to simplify, especially for the longer duration flights, right? But again, the way you've chosen to solve that and address that is very much in keeping with how the engineers would be working that today in our contractor world. The last thing I would say is from the lighting source, you're going to have to also recognize that the biology is going to require a spectrum of light. So it's going to be more than just one type of LED in one strip. You're going to be looking at a variety of different LED colors to be able to provide the light recipes that the plants will generally need. I will tell you that your watering concept is something that we had actually discussed with folks in one of an independent commercial contractor is how can you autonomously water plant pillows, for example, that we use on veggie. And it was basically doing something similar to what you've come up with, which was a manifold concept that you could have a robotic interface come in and basically do the watering by going to one spigot that routes the water to the individual plant areas. So that's very interesting. So I think from an engineering perspective, there's a lot of commonality of thought that you've applied to this thing, especially on your own, that I see in the engineering community that we work with. So kudos to that.
Thank you.
Have you tried building any of those things small scale yet, Alex?
No, I've not. Yeah.
Okay.
Yeah, I'm always going to be asking plant questions. Did you have any particular crop in mind when you designed the geometry of this?
Yeah. So last year, this design is pretty similar to my last year's entry. The plant that was kind of given to me, or like the guideline, I believe was red lettuce. So if I remember correctly, I did look up the height of red lettuce at kind of harvesting time. And did calculate that it would fit. It would be pretty close to the main kind of like LED central shaft, but it would be able to hit full ripeness before running into it.
Great.
Great. All right. Well, thanks so much, Alex. We're going to be moving on now to collegiate projects. So first up in that category is the Berkeley Seed Shuttle. I believe that's the GrowTech team.
Yeah. Let me share my screen. So hello, everyone. We're the GrowTech at Berkeley team. We're a team dedicated to the intersection between plant biology and engineering. We're proud to present Seed Shuttle V2.0, which is based on our Seed Shuttle V1.0, our submission for the Year 1 challenge. We'd like to introduce ourselves. We're a bunch of individuals who are interested in different parts of the GBE experience. Myself, I am interested in the space part of the competition, having been interested in space and entered in space competitions for many years now.
Hi, I'm Anthony. I'm a plant biologist for this team. I led year 1 of the GB contest for this team. I'm a second-year bioengineering student. Since I was 4 years old, I've been gardening, and coming into college, I wanted to pick up some engineering skills. So this was a perfect contest to engage in.
Hi, my name is Leonard. I'm a second-year CS student. I did the CAD for this design, and I like doing design in my free time.
Hi, I'm Matt. I'm a third year studying ECS and business. I worked on many of the automation aspects of this project. I'm also a hobby gardener and have a passion for aerospace technology.
Yeah, hello everyone. I'm James Rody. I'm a first generation and low income second year student at UC Berkeley studying integrated biology with an external interest in astrobiology. I have a background as a microgravity researcher since I was the co-principal investigator in an ISS experiment with the NCSSC, along with experience in robotics with my first robotics competition team. So the challenge, NASA's Vegetable Production System, also known as VEGI, which is shown here, credits to NASA and Dr. Joya Massa, currently supports 6 plants in an upward growth orientation, all in the same growth phase. Our goal is essentially to design a microgravity compatible plant growth chamber that maximizes production while also adhering to the volumetric constraints of a 50 centimeter cube and including all required features for plant growth such as light, humidity, air, nutrients, and temperature. So our foundational design seed shuttle, which won at the collegiate level for the 2019-2020 Growing Beyond Earth competition, features a 4-fold increase in production in comparison to NASA's VEGI, as seed shuttle produces a total of 24 plants and yields 12 mature heads of lettuce every 2 weeks, whereas NASA's VEGI system houses a total of 6 plants and yields 6 mature heads of lettuce every 4 weeks. We were able to increase the capacity through growing plants in different growth phases, along with taking advantage of the microgravity environment to allow different growth orientations.
Okay, so let's take a closer look at what this design is. So let's take a look at the right picture. That's a top-down bird's eye view of the chamber. As you can see, our plant of choice is lettuce, and the lettuce are growing in these different directions. The more mature lettuce heads are growing towards the corners, which have more room, and the half-mature lettuce heads are growing towards edges. And you can notice that the growth phases are staggered. And now taking a look at the left picture, you can see that there's this rotating central scaffold that allows easy insertion and removal of pots, and that the plants will be growing horizontally, thus taking advantage of the microgravity design. So how does this staggered growth phase work? So let's take a look at the first picture. That's after the plants have had time to grow. Now you see that there's 4 mature heads of lettuce. Let's harvest those. Now we're at picture 2. Picture 3, we've inserted new pots to take their place. And then finally in picture 4, we rotate the barrel scaffold by 45 degrees. So now that the largest plants are oriented towards the corners. And of course, we couldn't just have a design and not have plant growth experiments. So we went ahead and tried growing them. So in the first image on the left, that's our earliest growth experiment where we use red and blue lights, and we custom fabricated our own pots. But you can see that there aren't much plants growing and there's a little difficulty. So in the next iteration, we went with white lights, which are full spectrum, and we went with parts such as a plastic pot and a metal can for the reservoir, such that our prototyping process does not require a lot of setup. And with that, we were able to succeed in growing that registered red romaine lettuce to full maturity.
So now that we've talked about a lot of the components of our year 1 design, we'd like to emphasize some of the changes we made in order to automate our system, which include many changes to even the design of our year 1 design. So in year 2, we decided to focus on the automation of our system, and specifically we decided to maximize the responsiveness of our system to external changes, individually tailored experiences even to plants that are responding differently to our inputs. So in our system, we have a central processor, which will take in inputs from the camera modules, the moisture sensors, and even temperature sensors. And this provides enough input to allow us to get a good enough view of how the plants are doing, such that we have other systems that are interacting with the plants in an output system. And one of the most important of these systems would probably be the irrigation system, which not only provides water to the individual plants, but also nutrient delivery through the fertilizers that are embedded in the soil substrate. Other important systems, of which there are three, are the fan system, which controls the humidity, the temperature, as well as the air circulation. The barrel motor, which is a convenient feature where we can rotate the central scaffold, and the camera rail system, which houses two cameras at the top and bottom of our barrel, which can get a 360 view of how the plants are doing. We also have control of other components such as the LEDs, which we alternate based on the daylight cycle. So here's a view of the electronic scaffold. As you can see, based on our year one design, we clearly made some significant changes. I'd like to highlight some of the components that we mentioned before in a graphical sense. At the bottom, there's a water reservoir, and then you can see some of the outputs in the form of the yellow circles and the white circles inside. Those are the solenoid valves, which will be hooking up to our plant pots. And at the top, you can see some fans. And this is an automated system, and it also allows for the ease of removal of these plant pots, which can be latched from the top and bottom. So we went from 24 plant pots to 8. And as you can see, this is a cross-section of an individual plant pot. Before, we had 3 individual plant pots at every side of our design, but for ease of use, when it comes to watering, and because we now have the ability to provide water at a pretty dynamic rate, we decided to make some pretty significant changes. We combined the pots together into one longer pot, and we also shrunk the water reservoir at the bottom. We have a wicking system where the wicks go from the top all the way where the plants are through the soil substrate to the bottom of our plant pot. And that's where we're going to be pumping in water through the solenoid valves from the peristaltic pump. So not only does this system provide more space for the plants, for the plant roots, it also allows for more responsive wicking, because we can take the moisture sensors, which are capacitive sensors embedded inside the soil substrate, and directly use that to detail which solenoid valves to open and therefore which plant pots to get water.
So here you can see our irrigation assembly. The water is stored in a central reservoir shown as a blue oval in this drawing, and pumped using a peristaltic pump through each of the solenoids into each of the individual pots, where it's wicked to the plant roots. As a change from our previous design, as Yuji mentioned, we now have 1 pod per side of the central scaffold as opposed to 3, which allows us to save space and use shorter pipes. And then we use capacitive sensors to measure the moisture level and control the rate of flow to each pot. We regulate the temperature of the unit using fans to create airflow over the plants. Maintaining airflow is important because there's no natural convection in space, and without it, the plants would suffocate. So the fan it blows air out of the top of the unit, and temperature is regulated using feedback control with input from embedded temperature sensors. So our plant health monitoring system hopes to use hyperspectral imaging to check plant health and diagnose problems as they occur. A small robot with a camera is able to travel along metallic rails, shown in blue in this render, around the central scaffold, and tilt in order to get a 360-degree view of the plants. So in this render, you can see the robot as a small yellow box. And there is an imaging system on both the top and the bottom in order to cover both sides of the plants. And in case you wanted to build this yourself, here's our materials list. So thank you for your time. Here are QR codes for our year 1 and year 2 submissions. Are there any questions?
Have you built, again, any small scale parts of these, or have you tried just trying to build one cassette to see how that would work and how the water wick would run through that?
Yeah, to respond to that, we did build like a wicking system, and we tested out the wicks on a small scale. I'm gonna go to the slide where we showed that. So in here, you can see that there are the plant pots, and then we used a wick through the soil substrate, and we had some pretty substantial water reservoirs because we originally didn't automate the water reservoir pumps. Yeah.
Okay. And then are you using any sensors to see if that goes wrong in the future? Like, how are you checking that doesn't happen moving forward? Like, where it's over pumping or under pumping actually?
Yeah, so we're using a feedback loop using a capacitive sensor stuck inside the soil substrate. And because the capacitive sensor can detect when moisture levels get low, we can figure out when to pump in water and distribute it through the soil substrate. If you're asking about how this doesn't get waterlogged, we did test this out a couple times, and we figured out that usually the soil substrate doesn't get waterlogged enough to kill the plants, and also like it doesn't get waterlogged even if there's like an excess of water in the bed.
Okay.
So let me give you just a few comments. Everything you're doing is real interesting, and I think it's a very good approach in terms of taking something that currently exists like veggie and then trying to elevate the state of the art. Keeping in mind that veggie was predominantly designed to be a research facility that then has taken on a new role in terms of growing crops that the crew has actually been able to consume. It's still not an ideal concept. And so I'm going to throw this out there, not to change your design, but when this competition is over and the next phase is over, what I hear is that there's still an interest in biology, engineering, and astrobiology and moving on. So I'll tell you the kind of things that we deal with. First of all, I think it's a very positive thing to try to incorporate an imaging system of some kind. I think you'll find that a hyperspectral imaging system is probably more advanced than you're going to need to make the determinations you want and for the space that you have. I think that if you get a well-informed multispectral system, you can probably do that with commercial cameras that are available by using certain filters that target the specific wavelengths where we would expect certain stresses to be present themselves. So hyperspectral just has so much data, and there's probably a large part of the spectrum where that's just not relevant to plant stress detection. The other thing is that I'd like you to keep in mind for future applications that when I take these things on long duration space missions, I'm looking for reliability of the hardware components. So, and this will apply to all the projects. Things that are common failure points, I want to be able to minimize them if possible, and then also to be able to have quick access to them to replace them. So things like pumps and fans can be expected to be common failure points. So make sure as you go forward, if you can minimize the number of pumps, minimize the number of fans, or at least make them accessible to replacement, that's a huge plus. Then when I see a lot of water lines, I get concerned in terms of things like biofouling. If I'm going to be flying systems like this and I'm going to be taking them with me beyond the ISS, in a lot of cases, I'll probably have periods of dormancy where the crew isn't going to be present on certain vehicles where these hardware systems are. So the risk of contamination, biofouling, things that could muck up the systems is a real risk. We actually had a payload several years ago called the Advanced Biological Research System that had an internal water loop in it, and it was supposed to have been checked out and basically run every 3 months to maintain its working condition. And because of crew time constraints, we went like 8 or 9 months. And when we turned it on, the thing didn't work and we had to bring it back. So we have to be really careful about those things in future applications. I'm not saying that you can or should do anything much in this design, but keep those things in mind. And also, since I'm talking about future applications, we still really need to think about getting away from reusable consumable resources. So when I talk about soil in a lot of these applications, I would like you guys to also, for the future, spend some time looking up and trying to see if there are reusable media. If you can't, if you can't get rid of media completely, is there any kind of media that's reusable? Because I'm not going to be taking up bags of soil with me as I go further away from the earth.
Yeah, that's
when
a
we
really
fly,
good point.
yeah. So, and again, these are no critiques for your project. They just make me think of it in terms of everybody's thoughts.
I'm glad you brought it up because reusability is one of our design features. We just didn't touch upon it in this presentation, but now that you brought it up, the calcium clay is actually autoclavable. So if there's an autoclave in the ISS, you could take this calcium clay, and of course the pot should be autoclave compatible too, so that way you can insert the whole thing into the autoclave, and then once you take it out, it should be bacteria free, and you can reuse it for.
Yeah, so we don't have an autoclave. That's again is a big crew time constraint, even if we did have the ability to do something like that. And again, I'm not faulting your design or your concept. I'm just saying that for future applications. I think even if you could get something like this up into the ISS within the next several years, operating under the constraints that you've currently are working with, it's still an upgrade over veggie. So don't get me wrong on that. This is just for follow-on work past this competition, things to keep in mind.
I'd just like to make a comment that I really like to see this as an evolution from last year. I think this is great progress and a lot of interesting changes. And I really like the dynamic of your team. I like the balance between plant biology and engineering and programming. I just think you've got a good group.
Yeah, and let me jump on that too, Carl, because that is a key thing whenever we work projects that are plant biology projects at the Space Center. It's getting that team with the right skill set, knowing that the plant side of the equation, those people have to really set out the criteria that the engineers have to work to, and so there's definitely this pushback and this tension between the two sides, but it's precisely that thing that's going to lead to a realistic, incredible, and viable experiment.
Great. All right, well, thank you so much, GrowTech team. We're going to be shifting over to the UFL Simon team, led by Sarah Humphrey. Give me a moment to bring you up to the panel.
Okay, can I share my screen, please?
Yes, just give me a moment to bring you up to the
Got it.
to the panel. 1 second. There you are. Is there anyone else joining you with this?
Yes.
Okay.
Yes.
Okay, Simon team, Emmerich.
Emmerich, Stephen, and Jacob.
Great, we have the whole team.
And that's Jacob Mass.
Perfect. Okay, you can share your screen and begin your presentation.
Okay, let me do that. Perfect. Present. There we are. Hello, everyone. I'm Sarah, and I'm here with my teammates to show the Simon, the Spacefaring Intelligent Modular Nursery. So I'm a plant science major, and I'm interested in astrobotany. I competed last year, and I'm excited to learn more about automation and how to design these systems. That's why I'm here. I'd like to introduce my other teammates. Stephen, would you like to introduce yourself?
Hi, I'm Stephen. I'm a PhD student in the Agricultural and Biological Engineering Department at UF. yeah, just happy to be on this team. I worked on the imaging system for this.
Hi, I'm Emerick Larkin. I'm a PhD candidate at the University of Florida. I mostly do bioinformatics and microbiome research.
I'm Jacob. I'm an undergraduate student in digital arts and sciences in the engineering college. Just kind of interested in innovation and making. A lot of fun with this, yeah.
Hi, I'm Sean Romero. I'm a master's student here at Florida, and I'm just glad to be here on this team. Thank you.
Hi, my name is Jacob. I'm an undergraduate student in sustainability at UF, and I worked on the prototyping and design phase of the project.
Hello, my name is Oren. I'm also on the team. I did a lot of the CAD. I'm an undergraduate doing mechanical engineering as well as electrical engineering.
Perfect. Thanks, guys. So Simon is based on the seed shuttle design. We've redesigned seed shuttle from the ground up to optimize it for automation and to minimize the number of failure points. We optimized it with camera access, Raspberry Pi integration, sensor placement, and almost total control over the growing environment. For automation reasons, we have the 4 corners with different subsystems. So I'll talk you through them. These 2 corners, hopefully you can see my mouse, these 2 corners are for the irrigation system where we have pumps and the nutrient delivery system. In this 3rd corner, we have storage area for a lot of our hardware like microcontrollers. And for our 4th corner, we have our imaging system. Now, I won't delve too deep into the overall design of our chamber because you can see all the details on our Growing Beyond Earth page. However, I want to emphasize our irrigation system is completely removable and adjustable based on whether the Simon is in gravity, microgravity, or partial gravity like on the moon or Mars. Now, it's important to note that we use reusable, cleanable material, and this irrigation system is also very easy to modify and exchange for each crop. The most important part, however, of our design is, of course, the control system, because this competition is all about automation and control. So I'm handing this over to my teammate, Emerick.
The control system for Simon is fundamentally right now in its current configuration based on PID controllers at the set point maintenance level. We're also considering implementing some gain scheduled PI controllers to better overcome the non-linearity of some of these control actions, such as pH adjustment. We use a suite of environmental sensors, both gaseous and water-based, as well as the camera, as inputs into the PID algorithm, and actuators that include stepper motors, fans, lights, and peristaltic pumps that respond to these PID outputs. However, our current set points reflect the optimal production parameters for lettuce on Earth for this 30-day challenge, and we expect that these are going to need to be adjusted in altered gravitational or radiation environments, and they'll also need to be adjusted for different desired outcomes, potentially different flavor profiles, and then definitely will need to be adjusted between different cultivars and crops. The Simon analytical platform, which we'll talk about next, is capable of tracking plant health, and this will allow us to re-optimize these set points for these new environments, as well as our biological models that seek to gain a mechanistic understanding of how the plants are doing in the environment that we put them in. This creates a control system framework that will continuously create metadata associated with phenotypic information. And this data can then be used to validate and improve our biological models and just overall assess the performance of the Simon platform. These models can be used to improve the plants and from a place of mechanistic understanding. But as time progresses, because we have data of phenotypic information linked with the environmental parameters that we're giving them, we can then build data sets that can be fed to a machine learning based framework to further optimize desired outcomes in a little bit more of a black box type way. And this will improve how the system operates over time and space. In the diagram, you can see this sort of cyclical framework where we have a sensor driven automation system that's primarily based on Arduino and Raspberry Pi. There are wired and wireless configurations of the system. You can see some of the control boxes that are used for that in the image on the right. And that data stream is fed to the analytical platform, which then provides us performance metrics. And with biological interaction information from research, we can inform biological models and also tune our set points, which allows us to have flexible and optimized production and also a good platform for research. And that's for movement onto the analytical platform and imaging system.
All right, thanks, Emmerich. So to track plant health, Simon has an imaging system consisting of 2 Raspberry Pi camera modules modified with autofocus capabilities. So we have one camera that's fitted with an infrared filter and the other one without an infrared filter in order to produce 2 images for a total of 6 wavebands. So with these images, we take the pixel data and we have them undergo a homography transform in order to correct for a parallax error. And we also have a radiometric calibration step to ensure that these waveband values are standardized between images. And using these data, Simon can automatically calculate things like vegetation indices requiring the infrared wavebands, such as the normalized difference vegetation index, which is kind of a coarse way of evaluating overall plant health. So an additional step that we're also currently implementing is to correlate these values of the 6 wavebands with things like a ground truth phytochemistry to produce standard multispectral responses. Then when Simon takes images of plants, it can automatically compare some of these up-to-date images with known responses to common stressors such as tip burn and drought stress, and then provide corrective action by changing set points within its control system.
Cool. So we also wanted to design a graphical user interface for our system, so astronauts will be able to interact with this through a touchscreen on our lid. And so what you're looking at now, we have an interactive prototype wireframe, as well as a program in R that pulls data from a cloud and graphs it, as you can see on the top right. And our goal for the future is to program a fully interactable GUI in Python using Cami. But what you're seeing now are just a few of the pages of our GUI. We start on the top left with a main page displaying most important information and the most recent pictures of the first column. Then there's a bunch of other pages you can navigate to on the menu. You can see in the middle, there's the pictures page, which shows all the current pictures of all the columns in RGB and IR. And you could also click to an archive of all of the previous photos. There's a data log that shows all actions enacted by the control system and the internal program, as well as any other notes the astronaut makes. And then each of the subsystems will also have its own page dedicated to it with the data, and all of the variables are clickable, which will pull up, as you can see on the top right again, a graph that shows the data over time. And we think the GUI is important because it allows the astronauts to monitor all the data and judge if intervention is necessary at any point. All the data is archived and available for future analysis. And our GUI also makes this assignment a lot more flexible. It can be modified and adapted to other modules that we put in, other plant types and other environments in the future.
Thank you, Jacob. So we actually were fortunate enough to build a prototype of the Simon. Now, this took a lot of trial and error, a lot of effort went into this, and we ended up scrapping several parts and replacing them and finding ways to improve them. And that goes to the core of why we had a prototyping phase. We built this prototype so it could inform our future decisions on how to improve the Simon. We want to continue improving upon the Simon in the future, not only this coming summer, but also in future months and years. So someday it can be used not only in space maybe, but also at our university as a platform for research. So special thanks to our amazing mentors who have helped us get this far. And of course, special thanks to the contest organizers who have put so much work into this competition.
So I guess my first question is on the ground truth for the camera and the images. Are you doing that by training now, or is that like somebody on the ground will look at those images and start giving you
Yeah.
Some sort of feedback app or something like that where those images
So-
get sent out to several people.
Right. So generally what happens is in order to get this ground truth data, what you would do is you would scan the images of the plants and then kind of do destructive analysis on the plants in order to develop this standard model for plant response. And so you would do things like a HPLC in order to, get these biochemical data and use things like partial least squares in order to correlate that data with your pixel data.
Is that being done pre-launch, post-launch, or?
Yeah, so ideally that would be done pre-launch.
Okay, but there's ways for feedback loops on there. I mean, because I guess the data is somebody's going to the cloud, so the images go to the cloud too, so that somebody on the ground can say, "Hey, that's a new thing we've seen." They just train it on that.
Right.
Okay.
Right, and over time, we'll be monitoring different spectral signatures, and since we're measuring the performance of the crop and we know the environmental conditions, we can use machine learning to correlate certain phenotypes that we might see or certain plant responses that we might see. If we don't understand why they're happening, we can search for the reasons.
Awesome. And then the PIDs are generic, so they can all be interchangeable, like Rob said earlier, just on the ability to change things out. So all the PIDs are just programmable posts.
Yeah.
So they can be swapped out anywhere.
Yeah, sure, they can be swapped out. The control algorithm can be changed. PID is, probably the most universally applied control scheme for maintaining a set point. So I went with that because it's relatively simple to implement in Arduino. But it could be changed to something more advanced, like something that deals with nonlinear control. And we've considered that. But yeah, it's certainly changeable. We've approached everything with modularity.
All right, so I commend you on the fact that you're considering multiple water delivery technologies as part of this system. That's great. You're capturing all the, for lack of a better term, buzzwords that we would want to put into a plant growth system. So I'm talking about applications for machine learning. I've got an imaging system that you're far enough into considering that you're talking about NDVI with some intelligence, and you're talking about how I would basically train an AI system with the data sets. So this begs the question, you've got the terminology, you've got a prototype there, but now actually being able to use it in the manner in which you're stating, where do you on that? I mean, do you have the ability over time to be able to actually do this work? I mean, that it requires infrastructure that's above and beyond what I would assume you have available that's dedicated to this project. So where are you going to validate and operationally try to work through these issues and understand and learn more? I'm just trying to get a feel for that, because this is a very advanced way of looking at things.
Sure. Well, anything would require time. It's an iterative process, and since the automation framework is intended to be self-optimizing, that would require cycle after cycle of growth. I'll finish my PhD sometime in the next year, so I don't know how much time we have available for that, but the capability is actually pretty well fleshed out on the control slide. That shows the controllers interfacing with a data broker, which is a Raspberry Pi operating MQTT IoT network that interfaces with a InfluxDB server hosted on a server that we have. There's a data API built in Node.js, and that serves a GUI/analytical framework that's built in R. A lot of this stuff are principles that I use in my research outside of the Simon platform. It's also a sister spiritual predecessor continuation of a HydroPatrol platform that I developed as part of a grant with the Florida Space Grant Consortium. So there are capabilities that have been fleshed out in that just naturally integrate into our platform. So they're there and they work. The servers are up. I have all the sensors working. there can be multiple systems coordinating with a single Raspberry Pi and all that. So the capabilities there, I think the biggest hurdle for us would obviously be like manpower and time to actually, you know, over time have all these iterative things happen.
All right, so just out of curiosity, have you, does Dr. Rob Furl know about the work that you guys have been doing?
Not directly, I don't believe so. Certainly other professors involved in space sciences and space plant production at UFR, such as Dr. Corral, Dr. Selena Gomez are.
Yeah, the only reason I mentioned Furl specifically is because he's working with us on multispectral imaging and AI in terms of plant growth, and they're doing that work now. So there's definitely a correlation between what they're currently vested in and what you're doing. So, hey, this is all. Go ahead.
We also, in our department, have an entire center / system called the Spot Facility that's actually dedicated to the same thing. I don't know if Dr. Robert Frill is still focusing on Arabidopsis, but we're mostly looking at crops.
Yeah, he is right now, and we're talking about that in terms of expanding off. But I understand what his rationale is. Anyway, that's an aside. I'm really curious to see how this evolves over time, just because the technology you have there is very much in line with our thinking in terms of going forward. And good job. And I understand you've got a lot of folks on this project who are PhD level, soon to be PhDs. So that's helpful. But I think you're definitely talking language that I hear from our scientists on a daily basis. So that's good.
Thank you.
Thank you.
Thank you for the questions.
So I have a different kind of question. So you've gotten to the prototype phase, and I think I saw a photo with some actual live plants inside your system. And that's farther than our other teams, or most of our other teams have come. So I'm just curious about what kind of surprises you encountered when you actually put live plants into the system.
Well, we actually, those were for the pictures. I'm sorry, I thought we made that clear in the text. But we grew those plants so that we could transplant them in. And there was a setback. And so our progress was set back a little bit. And so we weren't able to grow the plants in the system at that point. But we're very close to being able to grow plants. So our main focus right now, in our main concern with growing healthy plants in the system, is our irrigation. Now, if we had NASA facilities and NASA specialists that would help us with this, then we'd be fine. But we have limited facilities, and we have to figure this out ourselves. So we want to take really slow, intentional steps with making sure our irrigation system is something that will be very consistent over time and very consistent throughout that entire column, that central column that we have. So I think that'll be our biggest challenge moving forward.
Yeah, to add on to that same question, we found it kind of a challenge to balance a potential progression to phase 2, where we're actually trying to get the most biomass that we can with a design that's actually realistically microgravity compatible, because that's very challenging, as everybody knows, and is certainly going to limit your ability to produce the most lettuce you can in 30 days during a challenge period here. So we recognize that, and that's one of the reasons why we wanted to go with some modularity, because if we're going for optimal production in a 30-day competition here, and we have a irrigation system that's strictly designed for, say, microgravity, another team that has an Earth optimized setup is going to beat us. And there's been some challenges in the irrigation system in that regard.
Join the club. That's our number one challenge, is irrigation.
Right.
And no worries, the plant growth data, that's on phase 2. So already you're pretty far along in advance, and you'll have the opportunity to do that in phase 2. So don't worry. Any other questions from the judges before we move on? Okay. All right. Thank you so much. That was an amazing presentation. We're moving on to the professional category. And first up is the Harvest Drawers team. Let me swap out the spotlight and bring the new team on just a moment.
Can everyone hear me?
Yes.
So I'm in Team Duluth, Harvest Drawers. So we have Danielle on our team. So we have Danielle on our team, who has experience in user experience and design and is kind of a plant expert. And then there's me, who works in engineering and data. So our design is based on an idea that we had about 1.5 years ago, and we entered in the first competition with the Harvest Drawers. We went through many different designs for ways to optimize the use of the space, and ended up coming around to just using standard different shells, because we realized that we're able to get a lot of area coverage for both lighting and the plants. So it seemed natural to kind of just stick with the standard drawers and kind of go for the safe bet. The kind of genius idea, though, was adding the slides to it so that a user can actually access all the plants in the system without having to try to reach back into the machine. So our design allows for a triple drawer design. So we can have either different configurations. So depending if you just want to do like a small area for sprouts and different growth stages, you can switch out the trays to get the maximum use out of that space, or just set them all equal heights and go for kind of a one-shot plant growth cycle. A lot of this design is just adding on to our original and taking care of problems that we found that we had from the first version. So with our first version, we sent water to each tray, and the water would stay there and would lose oxygen, which we think the roots didn't like, and kind of slow down the growth cycle. So we're adding an air bubbler system to make sure that each set of plants has the amount of oxygen they need. And then we're going from a standard off-the-shelf kit for watering the plants to a complete custom system using Raspberry Pi, like most of the other teams are using, and adding all the various sensors and so on that go along with that. Materials, we try to stick to very standard things for as much as we could. We end up using some custom sheet metal, which was fun to use, and using Fusion 360 and Python and Adafruit Ada.io also. So moving on to the renderings of it. So we added on, you can see on the bottom section here, we added a ruler onto each of the plant areas so that the cameras can view the plant sizes and growth. The camera would be a fisheye lens, so you can see the complete picture of all the plants. They won't necessarily be scaled the right way, but you can use the ruler to figure out the scale or modify the images back to flat from the fisheye. And this allows for a full view of all the plants growing all at once. And then for measurements, there would be a IR distance sensor, so you can view the height of the plant growth from the top. So instead of having two sets of cameras, we could just use the same sensor, or use a sensor just to view the height growth as it goes up, and view the plants to kind of take care of that measurements scenario. With our lighting, since the lights produced a lot of heat, and last time we had temperatures reaching up to 100 degrees Fahrenheit inside the system when it was fully enclosed, we tried to maximize the airflow through everything. So using sheet metal and having the water reservoir on top of that, it acts as a really great heat sink for all the lighting, and then the fans blowing over to also help with that. So here's the control system in progress. We're using just a standard computer power supply since it has the logic level voltages you need of 3.3 and 5 volts. And then 12-volt rail is powerful enough to run the lighting system. On the top, we have the Raspberry Pi hooked up to a relay bank, which will control the lighting, the fans, the solenoids for the water system, the main water pump, and we're assuming that there'd be a water line feed to the system since you would need more water than the system could hold to water the plants for that given period of time. And a nutrient reservoir, which we will then pump into the main line for the watering system. So you could just have a dose of the nutrients since it's relatively concentrated, then just send that through the regular water lines. And then the bubbler system will take care of all the mixing of the nutrient into the water once it gets to each separate tray. We also end up using the AeroGarden plugs that they sell with their standard kits. Since we had problems with germination time, we were trying to figure out why our plant system was taking closer to 5 weeks or 6 weeks versus 4 weeks when we had our initial harvest drawer. And we noticed that germination was taking up to a week just to get sprouts with using aquarium foam. So we found that the AeroGarden plugs are very, very reliable for germinating the plants and thought that'd be a great way to save some time during the grow process to maximize our growth. And that was averaging around 3 days for germination versus 7 days. And that's the overview. Any questions?
I think it's real interesting to see a compact design like that that's all self-contained and you know it's actually growing plants. Have you put that in a cabinet type system to block off the entry as if you were to actually configure it in a vehicle, so to speak, and see how it performs?
I have not. Our first version, we had the sides closed off, so it was closer to that configuration. This time we kind of opened it up to increase the airflow, but in the future, we do want to switch out the tray system instead of having the electronics all in the back. We want to switch that out to a drawer system so that a user can access everything easier. Because right now you need full 360 access.
Yeah, that is very much, when we start talking in the future about how do I get robots to interact with this system and maintain it, that again goes into part of the challenge we have in terms of looking for the common failure modes and making sure that they're accessible to some future robot interface. And most of that stuff you would want to put on the front someplace, but that's also where you need to access the plant, so there's a competition for that prime real estate.
Yeah, definitely. Yeah, but we're thinking a drawer system would help maximize that. Since right now we have, I think it was about 10 centimeters or 8 centimeters of the back areas taken up by the electronics. So
yeah,
swap that for one of the plant drawer heights, then we can expand it back further.
Right, and you're dealing with the exact same thing we do, and that is that I'm given a certain amount of volume, and I think, and I didn't make this point earlier, but I think it's good to consider is that generally when we grow plants terrestrially, we talk about growth area because height isn't necessarily an issue, but when I'm on a space vehicle, it's really a volume utilization issue. And microgravity potentially, because you can see in the presentation today, frees up alternative ways to actually orient and use that volume. But we constantly get it's a struggle for the engineering side as to how do I provide the most space to the plants and not have the infrastructure and the hardware that's needed to support them cobble up a lot of that usable growth space. So it's all part of the struggle.
Yeah, definitely run into that quite a few times.
Yeah, I was curious about whether you found that the high temperatures affected plant growth when you tested your design last year.
It seemed like there was some stunting of the growth. I can't say necessarily what the factors were. We tried to add more ventilation, and it seemed like the plants seemed to respond better to that, but I can't say confidently if that was a big factor or not. I think looking at the data, they seem like this type of lettuce like cooler temperatures in general, if I remember right.
Are you also looking at the intensity of the light?
Yeah, our light, it seemed like, I'm not 100% sure if this was true, but since this red lettuce seems to get redder with more light that it gets. Our last batch, it was fairly green in color. So we're thinking that we were actually lacking amount of light then. So we added more lighting capability this time.
Okay.
And I saw that some of the teams too were using the 3 reds, 1 blue light. And we didn't really have any success growing with that. The plants seemed to respond very long and stringy, thinking that maybe they're hidden because that response to red light, they try to grow up taller faster. So if any other teams are running into weird stringy lettuce, it's probably the lighting.
And how were you checking the O2 earlier? Like you said, you saw that problem. How are you tracking that?
So we'll be setting up the I2C sensors as the protocol, and we'll be off Adafruit. Actually, I don't think there was O2 in our setup, but just CO2.
Okay. And are you running inside the cassette or outside the cassette?
So we'll be just putting it off the back of the system was our plan.
Okay.
And then we have it set up with using DIN rails that are commonly used in like PLCs and other automation, just so that it's easy to modularly move things and snap things off and off, move parts around. And it seemed very nice for doing quick prototyping.
Thank you.
Thanks.
All right, great presentation, Team Duluth. Our next team is actually a very, very unique team, definitely a different team than anyone else that's been presenting. So we're really excited to hear about Hugh's microgreens. And I will bring you up to the panel now.
Thanks, guys, very much. Can you hear us?
Yes.
Okay. So we're in the professional category just because we didn't have a category for 6-year-olds. But here is our presentation. Let me, let's get the sound to work. The sound isn't working. I'm so sorry. Share sound.
I can't really hear you.
We're Team Astronaut Microgreens.
My name is Megan Hughes and I am 7 years old.
I'm Jeff Hughes. Neither of us are astrobotanists, nor are we in high school or college or professionals in any area related to any of this. Megan came up with an idea that allows the production of more than a ton of vegetables per year out of a 50 centimeter cube. Just add water and electricity. I've named it the Megan method, a sponge diffused osmosis variation of the Cracky method.
Microgreens are young vegetables, harvested just after sprouted seeds have developed their first leaves. Our favorites are radish, sunflower, broccoli, mustards, and arugula. Not all vegetables make good microgreens.
I'm a meat and potatoes kind of guy. I find microgreens addictive. They're a lot more flavor intense than more mature vegetables. According to the NIH, just days after germination, a plant the size of a 4-leaf clover can have more nutrients, vitamins, and minerals than a head of broccoli.
They grow very densely. Eaten in bulk like you see here, they have a texture a lot like lettuce.
A 10 centimeter coconut coir pad with 1 gram of tatsoi seeds will grow 50 millimeters and yield 50 grams in 10 days.
Microgreens are a one-touch crop. Seeds placed on a reusable pad only need water, light, and air to grow. Put them in a Mylar bag. Leave them alone. Come back in 10 days, pull them out and eat them, roots and all.
By growing organic, hydroponically, and eating the lower stems and roots, we beat industry standard figures for commercial productions for microgreens by approximately 20%. The roots are delicious and nutritious, but are generally discarded commercially for aesthetic, time-saving purposes at harvest, particularly in soil-grown environments. Eating the lower stems and roots also reduces waste and helps with cleanup. Managing more than a ton of crops in a 50 centimeter cube can get complicated fast. Nominal values based on rounded numbers are used for simplicity. The system will need to be scaled to less than 100% to get everything to fit, plus a margin of error.
The system scales easily.
We're also going to assume a homogeneous crop for these examples, which isn't what we would do in space, it just makes the example simpler.
We can take advantage of microgravity and stack the pads. Seeds don't take up very much space for a couple of days. We put a new pad on the bottom of the stack every day. When day over day growth declines, we harvest from the top.
On day 10, we have a stack of 10 pads, 25 centimeters tall. We have 50 centimeters to work with in every direction, so we can have two 25 centimeter tall stacks. The pads are 10 centimeters square, so we can pack them 5 wide and 5 deep for a total of 500 pads. 500 pads is a lot to manage, so we'll put 5 pads in a bag and then just manage a system of 100 bags. Each day, we can harvest 10 of those bags for a total of 50 pads.
50 times 50 equals 2,500. 2.5 kilograms per day times 365 days equals a little more than a ton a year of vegetables.
Taxaway data was volunteered because results made for middle of the road and almost magically round numbers. Harvest to seed ratios of 50 to 1 grams, 10-day height of 50 millimeters, and approximately 1 ton per annum outputs. If we were to prioritize mass and the astronauts never tired of Chinese cabbage, Tokyo Bacana yields 80 grams in 10 days, or 60% more than tatsoi. Now we've introduced multiple varieties of plants to the system. So of course,
Astronauts get their choice of vegetables every meal. 50 pads for 6 astronauts, 3 meals a day. Each astronaut gets 2 to 3 pads per meal. Extra astronauts bring extra bags. Coconut core is hardy, gives the root something to grab onto. Sponge is lighter, can precious for travel, and hold more water, but it's fragile. We use the sponge to supply contained water to the core.
the capillary action from the core wicks water from the absorbent sponge. Then we put it all in a perforated mylar bag with an LED strip on top. The minimum electronics for the system consists of the LEDs and the wire to supply them electricity, connected to a timer that's on for 18 hours and off for 6, inclusively weighing approximately 205 grams.
Materials for the 100 bags weigh less than 3.5 kilograms and can be stacked 2.5 inches tall for transport.
Volume inside or outside the cube can be pre-allocated for fragile plants like amaranth or chives, and/or a pouch can be used for more water-hungry plants or those with unwieldy roots. Cages work independently from pouches. A single-seam mylar tube ducting system with a thin piece of plastic, shipped flat, spiraled up and secured inside will have a minimal impact on transport weight and volume. A small fan will blow air into the supported tubing. Another one of Megan's ideas was for astronaut gelatin salad dressing. Gelatin can be flavored savory as well as sweet and can be used as salad dressing. Ranch, Italian herb, and homemade flavorings were tested. Instagel has the same properties as standard boiled gelatin, but doesn't require high heat to become firm. So it's easier to make in any environment, and the gelatinized salad dressing sticks to microgreens really well. Astronaut Microgreens is a just add water kit with everything you need to learn about microgreens and general plant growth that would be for sale in science-oriented gift shops around the world next to astronaut ice cream. It would contain seeds, core, sponge, a mylar bag, LEDs, a tray, and astronaut salad dressing. Materials list for this project include seeds, the coconut core, the compressed sponge, which is also available as medical sponge, mylar bags, PCBs, which can be farmed out to numerous sources or handmade, wire, wall wart, timer, connectors, and LEDs are commodities available from DigiKey and other sources. Thank you very much. We're happy to answer any questions you may have.
Okay.
I just want to say that was amazing. That was awesome.
I guess.
Thank you. Microgreens are delicious, Ralph. We're going to go to town on this one. They're really, really good. I've been sitting here eating half of my demo while we were watching everybody else's presentation.
So we're getting ready to, we're actually funded this year to do some organoleptic and testing with microgreens. We're looking to fly microgreens. We're big proponents of microgreens. So you don't have to sell me on that. We have to prove them. And the challenge is going to be, you know, food safety. That'll be a huge challenge to overcome, because right now we haven't grown microgreens in space. We know that sprouts are a different story, because sprouts, they like to, and you mentioned this too, you like to consume the roots, but there's an issue with the microbial content for different pathogens that I'm told. So we have to be sure that that's not going to raise its head. And so I know that in talking to our plant scientists, everyone's pretty much going down the road of actually having to, you know, mow the lawn, so to speak, and cut them and harvest them that way, and not get into the roots. So that might just be a one change. But the thing that I was most impressed with about your guys' presentation is it came from an angle that is where we have to defend ourselves, and that is, how do I maximize the edible biomass output for a given volume of space? You know, for anything but future sustainable missions, if I have a prepackaged food system that's still viable, the big challenge for us is, why should we invest in the infrastructure to grow food when I can, in place of the volume and the mass it takes to fly that infrastructure, I can just fly more prepackaged food. So you actually come at it from the standpoint right out of the gate that you're telling us what the amount of edible biomass is, the productivity, and you're looking at it in a way that a group of NASA managers would try to attack an idea. And so that was a huge positive. We still struggle, just like every other presentation we heard today, we don't really focus on that aspect of it. I really think that, you know, we need to talk about productivity versus consumables and reliability, and you kind of hit the ball out of the park when it comes to that approach. So what I heard is really interesting. You've got a very lightweight, compact way of growing microgreens. It's a novel and potentially could be, you know, I think I'd have to see how you apply it. It's not going to solve every challenge, but in a way, it's a revolutionary way of looking at things. The other thing is that, you know, that you have to address the negatives. If you're going to grow so much, I don't think you need to grow so much in these large quantities, because now you're going to have to worry about how do you store it and keep it fresh. And I know that there's a lot of progress being made terrestrially in marketing and selling and distributing microgreens and keeping them fresher longer. But I don't think you're going to need those large quantities. We're talking about supplemental nutrition. We're going to be feeding a crew of 4 to 6, not, you know, 2 or 3 large restaurants. So
So 1.5 of these cubes would provide 2,000 calories for an astronaut in any given day. There's no storage whatsoever. You pull them right off the pad and eat them directly.
Okay,
is the way that we had. Yeah.
Okay, and that's great. So you've got it there. So I you know, I have nothing. I have very little suggestions. I would love to see this go forward. I don't know how it fits in with, you know, robotic applications. So you're going to have to consider that. And since your infrastructure to grow is so minimalistic compared to a lot of the other approaches that we've seen, and today and we in NASA have taken, you probably want to focus on seeds and the viability, because that would be the potential Achilles heel, is that if I'm going to be flying these things long duration, we have to make sure that the seeds are viable in this radiation environment. So you might want to do some research as to how you would transport the seeds, what the weight of the seeds would be to keep a certain output per day for like a 3-year mission, that kind of thing, because those will be the follow-on questions based on your productivity. But super interesting talk, and I'm sure that this wasn't basically your idea. It was basically Megan's, I would imagine. So
I was doing the same thing that everybody else was doing, the convergence of last year's winner, Mr. Arnold there, and she comes in and goes, "Hey, Dad, that's really complicated. Why don't you just put season back?" Right? Okay. Let's give that a try. 50-to-1 yield ratios, even if you get 80-90% termination, I'll put the seeds in the lead bag, I guess. The red, outrageous red, isn't as good as the tatsoi or the Tokyo Bacana cabbage, right? It's 25-to-1 seed to yield ratio. The tatsoi is 50-to-1. The cabbage is 80-to-1.
You're focusing, the key thing, and I will tell you from the food system folks, which ultimately in all these projects and everything we're doing at NASA, what we're doing is we're trying to, produce a food source for Cruz. And where we should focus on in that is variety, palatability, texture, all those things, because ultimately the astronauts have to want to eat it or they won't eat it. So we can talk about all different exotic type of foods, but if they're not going to be something the crew is going to want to eat, then they're not going to. And if it's something that they're not going to want to participate in the production of, then they likely will have, find less time made available to do that. Psychologically, it won't be of interest to them. So it could be a stressor in and of itself. So variety is key. You've hit the nail on the head with the variety aspect of things. And so what we're trying to do is prove that microgreens really, are as promising as they would appear in spaceflight. And that's why we're going to be doing early research in microgravity with them, just to make sure. So yeah,
I'm going to make it my life's mission to get you to enjoy some microgreens, Ralph. You and me, buddy. I'm going to send you some.
Let me tell you, this is interesting, because about 3 or 4 years ago, we hadn't really explored microgreens. We had a new guy in the office come in, and he started, touting all the benefits of microgreens. And a lot of people, at least in Florida, in the NASA management, weren't really exposed to microgreens. They really didn't understand them. So we would grow them. And when high-level NASA managers would come down to Kennedy, we would have microgreens there for them to try. And they were blown away by the taste, especially when you start getting,
the spicy ones. They're delicious. They're addictive. Yeah.
The mustards, wasabi ones with this flavor and this explosion of flavor. And that sold them on at least letting us try it, because they really weren't aware of what microgreens were. So a lot of it was just getting the word out. You go into these high-end restaurants and microgreens are available. They're on the menu, but a lot of people just don't frequent those kind of establishments, and it's not pervasive in society yet. So it was a matter of selling the idea. So we've sold the idea now. Now it's proving that the idea is going to work, especially from the food safety perspective. That's ultimately the gate that everything we go through has to compete for. In any of these projects, if we were to take any of the projects that any of the students have worked on today and adapt them and ultimately fly them, we're going to have to demonstrate that the output that they produce is food safe. And I've heard one presentation today talk about microbiome. That is a hugely important aspect of everything we do, because ultimately the microbiome of the plant and the media is important. The microbiome of the plant growth facility is important. And the interaction of that microbiome with the vehicle and the crew is all important. So it's a complex set of problems we deal with. Just production is just one aspect of it, but the food safety is ultimately the final gate that makes or breaks any of these ideas.
if we can keep it relatively sterile, right? The pad, the water, their individual packages, and so forth. So the contamination issues that have been troubled more mass production things, I think we can take care of. I have been eating the roots and stems, and we're still alive. I don't know. I know it's anecdotal, but we're doing all right.
The reusability of the pads. What's
the interesting thing is that
Go ahead. I'm sorry, Ralph. I am listening. Go ahead.
Well, Carl was talking about the reusability of the pads and the cleaning. That's something you'll have to consider for sure.
Yeah. Okay. So they start out. So we're mixing the core and a sponge, right? So they start out at 3 millimeters. I have used this one 38 times, and it's still in visibly relatively good shape. It's hair. Think of it as hair. If they get a little fuzzy, this was the fuzziest I could make it, was this one, right? Gets to about 8 millimeters wide. You get it wet and you compress it in a sandwich and they go right back down to 3 millimeters. We joke, we could add a little H2O2. We could put it for a cycle in the airlock. I think there's a handful of ways that we can make sure that these things stay okay. We really do, if we, one way or the other, we have to rip all of the plant and the roots out. And when we go to eat it, even if we have to cut off the base for any reason that we need to do that, it gets most of it out of there, and then the rest can be dealt with. There is a little bit of, sometimes the plants break if you get a little aggressive yanking them out. So you just flip it over and yank it out from the bottom. I'm also playing with, I know this gets a little, out of scope here. Please don't turn that off. Sorry, just a second, Tweety. I'm also playing with carbon-filled nylon 3D printing these things so that we could tear them apart. I've got pretty close to the coconut core. I'll just show you the difference. I can get nylon to act a lot like coconut core hair. And I think we could print it and then build something that we could rip open and really get every little piece out and put back together.
All right, so let me just, I don't want to take up too much time, but a few points. First, on your 3D printing, we do have potentially, we could use it this way, the capability to 3D print these mats and then actually recycle them in the 3D printer. I've been told that they will handle inedible biomass from plant material as part of the recycling process, that wouldn't be a significant concern. So that might be a problem. That's not a problem. When it comes to the other thing I want to mention is when it comes to the food safety aspects of things, we have to recognize that when it comes to astronaut health, the flight safety, food safety people are far more conservative than even the food safety people who work and look at produce coming into supermarkets in the US. They see microbial count, they see fungal counts, and even though they may be non-pathogenic, they may have no impact on human physiology in terms of making people sick. They see counts and they don't like to see counts. They don't necessarily know what that means at a science level, so they get very leery. We've actually grown plants on veggie, and we have had to go and sanitize everything that we grow with Prosan wipes. And doing that, even though what we've demonstrated is that a lot of what we grow on veggie and space is actually cleaner than what you can get in the grocery store. So we have to recognize that there's a different standard when we start talking about astronauts, especially when they start getting further away from home. We have to be really conservative as to what it takes to keep them healthy.
Brenna?
Great. All right. Well, thank you so much, Team Hughes. If you can actually stop sharing your screen, and then we'll move on to the last presentation for today from Jack Hahn.
Unmute. Thank you to all the participants. It's really been enjoyable watching and seeing all the advancements that have taken place in this last year. Am I on screen sharing yet? No.
Not yet. We don't see your screen yet, Jack.
Okay. There we go. Share. Okay, am I there yet?
Perfect. Yeah, we see it.
Okay. Yes. Yeah, I started out thinking about the hydroponics initially when I started reading about the imbibition problems of the aggregate materials and feeding the nutritions to the plants through that. So I've pretty much stuck with a hydroponic approach. And what I wanted to do was be able to get plants that can move individually, because that would optimize the available growing space within that 50 centimeter volume, and move those plants to an increasingly larger growing level. So I designed a root chamber where each plant will have a 6x5 cylindrical robotic root chamber, which moves horizontally and vertically on a magnetic field generated by a printed circuit board substrate. And the plants would then be fed hydroponically as they advance through 3 different levels, which will allow for 12 mature plants to be harvested every 10 days. In the sketch and diagram here, I initially started with a tray design like the harvest group did. That kind of inspired me to do that. And so I grew some plants sampling that in a tray, and then figured out the dimensions of the 3 levels, starting with the mature plant of the outrageous lettuce. Needs about a 15 centimeter height and a 10 centimeter diameter space to grow in. So working with the volume available, I picked out 75% of the area, the volume, for a grow space, with 25% to the left being the utility area. With the available space left, I then created the second and the first levels. The first level would be the first 10 days where germination would occur in 10 days of growth. And then those would advance down to the second level for another 10 days, and then to the third level for the last 10-day period. I allowed like 2.5 centimeters of space for the lighting and for the microcircuit boards. And you'll notice from this drawing here, as well as maybe the photograph on the side, the starting level has 16 individual plants, whereas the subsequent levels have 12. So I was anticipating, since I had to use that vertical space and the plants would still be so small, I could accommodate more plants and possibly pass the smaller ones out, or if some didn't germinate, I can still advance 12 plants to the second and third levels. And this was a look at the initial irrigation plan from the back side, which was the challenge that many people have been dealing with in the irrigation. I ultimately, for this model, had to, for reasons I'll describe later, eliminate the rigid plumbing system and go to a flexible tubing system. What was part of the inspiration initially for trying the hydroponic system was believing that NASA had already solved the flow and microgravity situation with the advent of their space toilet. So what you see here is a reservoir which would hold the water and nutrients. It flows up into the root chamber, travels through, goes into the separator where it separates out any air and recycles it back into the cabin, and takes the fluids back into the reservoir where it gets repopulated. And that would also be a feed location for additional nutrients would be fed into there. What I ended up doing on this model through several iterations was I had to get 2 pumps, one to push and one to pull, because I want to keep a negative pressure inside the root chambers, so we're avoiding water droplet escaping into the environment. There'll be foam plugs that'll actually go in the top of these holes right here in these root chambers. And with the negative pressure, hopefully that should keep it from escaping into the environment. And when I put in the second drain pump, I found out of the 3 pumps I had to try, this one was a non-priming pump, so I had to put it below my reservoir level for this model. So, but there is room to accommodate it in here if I had a priming pump, self-priming pump. Also, you can see over the top here from the drawing, this space right here is a vertical shaft area, which will allow the plants, once released from the manifolds, to go down to the next level. Obviously, the key component of the design is the root chamber itself. One of the issues I was considering was how to get the water across the roots in microgravity. And not knowing exactly how the flow would be, I figured it at least needed to come in from one side, which plugging into the manifolds would require both inlet and outlet to be on the same side, but to divert the flow to the opposite side of the chamber so that when it goes out into the foam area, it would by necessity be pulled across through the negative pressure to the drain system and engage the roots in that endeavor. I also, as I was designing this, realized I was getting some more puddling in the bottom of the chamber. But as one of the earlier people mentioned, the puddling didn't seem to be too much of a problem in the previous design, but I didn't want to have too much in there to actually flood the roots. So I put in a scupper that would cause the flow to come right off the bottom and minimize any puddling that could occur in the chamber. What inspired me to come up with an individual root chamber was, if you'll allow me, this one little video that I saw that I'd like to share with everybody, because I think it has
robotic technology has come a long way in the
an
past
increasing ability to provide options for harvesting in the later stages, as well as moving the plants through the chamber. And if you'll look at this and just kind of read at the bottom what's going on, you will see the immense capabilities and accuracies that are achieved, the flexibility of movement in multiple vertical, horizontal, and even bendy directions. The speed that they achieve is of no particular concern to me at this point, but also the uniform movement they can have through multiple platforms. Now here's where it starts to get interesting. When you see it, multiple robots going and picking up components, glue, and sticking them to the wall, starting to build structures. I can imagine these activities being used to actually engage in harvesting and picking up the plant root chambers as part of the harvest sequence. This to me was really the most interesting part, how they were able to construct this trellis. I'm trying to get my screen back here. Am I still connected?
Yeah.
Okay, I may have.
You may want to stop sharing screen and then try relinking the share screen so that it goes to the proper window again.
Okay. Well, let me see. Okay, here we go. What determined the sizing I chose for the root chambers was the previous experiment where I had done the tray, which had a common root areas, which had a 5 centimeter available space in there. So I figured what I saw when I harvested these was a significant difference in the root structures. These came out of the same location. One was very small and one was very large. There may have been some uneven puddling in that tray that caused that, but in either case, the leafing appeared to be pretty vigorous. So I thought that was a good enough indicator to proceed with this size of root chamber. And going forward in the next iteration, if this is successful in growing plants again, I would try to reduce that and see how low you could possibly go, maybe down to 4 centimeters, 3 centimeters, because that'll gain a significant amount of an additional 2 centimeters of height in the final grow area by just reducing the root chambers by one centimeter, excuse me. The parts list was extensive and I had to do a lot of searching around to find those through Home Depot and Amazon. One of the problems that was mentioned before was the germination period. And I heard something about a sponge, which I didn't pick up completely on, but I also observed that being a problem of taking a week to germinate. And when I covered the tray with a plastic clear cover, they germinated in 3 to 4 days. So for this model, I also devised a little plastic cup, clear plastic cup to be put on for the early stages that I believe will probably enhance the germination as well. Although now that sponge issue sounds interesting as well. The drain pump that I had to get here, which is also the feed pump, I had to design this manifold structure to suck in from from the 6 different manifolds. Actually, there's 12 manifolds, 6 for feeding and 12 for removing the fluids. And one of the design limitations here was had to deal with 80 different couplings. So I had to find a cheap enough coupling. These were under $2. They're inline couplings because I need an in and an out for each one. But ideally, in the final solution, they'll need a 0 drip automatic coupling, which will allow these to move from location to location in the design. Some additional renderings I had in designing the root chambers, which thanks to Fairchild and NASA's efforts and funding, gave me the maker grow space in the garden to go and work at to help create these designs. Otherwise, this wouldn't have happened and I wouldn't be involved at all. So thanks to you all for allowing me to do that. It's been a lot of fun doing the project. These are some of the subcomponents that you're seeing here of the root chamber and the irrigation system. So available for any questions. I could address the lighting as well. It did use a 660 and a 440 angstrom lighting, which produced those results that you saw before. So I stuck with that lighting system on the 3 levels going forward with this system.
Any comments from the judges? Questions, comments, concerns?
Well, I think Jack's really deep diving into some of the specific challenges that we'll deal with when we start talking about water delivery and hydroponic systems in microgravity. Also the cup for the germination, that's a common tool I've seen our plant scientists use during the early germination phases to make sure there's enough moisture there. So that's spot on. It's for one person, right, Jack? It's just you working this?
Yeah, I wanted to have it part of a team, but because of COVID and the delay in putting the facility together, I've had to go it alone.
Right. That's a very impressive scope of work challenge, taking on different challenges and coming up with solutions and then trying to integrate it together. That's pretty impressive.
Yeah, I failed to mention I had to use, because my Arduino coding skills were not up to the level yet, of using 3 individual timers, because the Arduino Uno has 3 timers in the board that could be used to time the lighting and the 2 pumps, which have to be on different schedules, sequences. So I just had to go out and buy 3 timers, which are also integrated in the available space.
No, again, I'll stress, I've seen this a few times in the presentations today, that there's engineering solutions being proposed to certain aspects of the overall challenge that are on par in terms of the kind of things I would expect from the engineers that we actually pay to do this kind of work. So to me, that's pretty impressive.
Thank you. It's fun too, trying to address the challenges. And there's many ahead. Stopping leaks in the system, for one.
Yeah, Jack, I know you've been 3D printing parts here at the Innovation Center. How is that going with the leak, getting the leaks and getting all that to pump through? Is that working using the 3D printers and doing the works you've been doing?
You're asking how is the flow working right now?
Yes, sir.
What's happening, I'm trying to balance the flow. If you'll see right here, there's a manifold flow valve that has individual controls. So my challenge this week is to get those adjusted to get the right amount of flow to each of the 6 levels on the input and the drain output at the same rates, or actually have the drain at a higher rate so that these don't flood. I'm getting an uneven distribution of the fluids at the current time that I'm going to be addressing this week.
Are the tubes the same width?
No, I got a 4 millimeter input and a 7 millimeter drain. Although the pumps are of equal pressure or equal pumping ability, they are adjustable flows, and I do have an individual flow rate adjustment on the inputs as well through that adjustable manifold.
Okay.
Jack, I know you mentioned this. I didn't really pick up. What exactly is your lighting technology? Is it strips of light?
It's the strips of light. Let me see if I can show you that. Light manifold, cube, drain manifold. Connection.
Okay.
Like you see here, this is the top panel, which also has a fan, and there's a shaft area in the design below that, so it'll pull area from the outside environment through into the closed corner to create the airflow across the plants and exhaust through the top. The top panel is actually a 3:1 660-440 angstrom lighting, which I got out of China and I couldn't get any more, so I had to switch to a 4:1 because that's all that was available this season, and laid out the patterns a little bit differently, but basically filled them up with as much lighting as I could and have dimmer switches on those, so I'll be able to adjust the amount of light. I would ask your opinion of the leaves that you saw before from the outrageous lettuce, which was done under this lighting. Do you consider those need some of the green wavelength as well as the 660-440?
Boy, it's really hard to tell looking at the picture. Looks like your intensity might not be that great just by the way they're growing.
Well, what I decided to go with this again for was that this is the level that did produce those plants that you saw earlier. And I had bought a system that I put in before, which was too intense and actually created too much heat. So I opted to do this system rather than the other one that I purchased.
Yeah, well, that's always going to be an interesting trade-off when you have lights that are so close to your plants, that balance of intensity and heat that they're generating. Yeah.
So I can turn these down to be pretty cool, but I wonder, I'll have to just trial and error, see how that affects the growth.
Great. Thank you so much, Jack.
Thank you.
All right. Well, spotlight. Perfect. Okay, so we want to just say thank you so much for all of the hard work and dedication that each of you have put into these projects. We selected each of your teams from over 60 submissions on this round. And so your presentations just reinforce that these selections were the right ones to make. It's just really, really impressive to see how far you all have come along in the middle of a global pandemic, in the middle of dealing with all these challenges that are going on right now. The fact that you have been able to make real engineering and real science and real collaboration happen right now is just an inspiring feat. So we are really excited to announce that each of your teams will be moving on to phase 2. And you are all finalists moving forward. And to that end, you'll notice that the numbers of the finalists is a lot less than last year, right? We're looking for more progress each year, and the categories are even stricter as we move from year 1 to year 2 and to year 3. The requirements are going to be higher and higher each time. So we are making the announcement that we'll be opening up an extension for 2 weeks to give chances for the other participants in this year's challenge to refine their projects and resubmit to join you all as finalists to move on to the next phase. But we wanted to give you the heads up that you are moving forward to the next phase. So a huge round of congratulations to all of you. Carl, do you want to make any closing statements or general observations about everything that we've witnessed today?
Oh, just to say I'm so proud of the way this has come together, and I'm proud of all of you, and just what Tom said about the challenges that you've all faced, and we've gotten some great new ideas. Every time we look at things like this, we get new ideas and things that we didn't think about before. So great work, everybody. I can't wait to see what happens. As a botanist, I'm always excited when real plants get into these systems. So I think the next round is going to be just a lot of fun, and we're going to learn a lot. So thank you all so much.
Yes, very impressive for all the teams, especially the younger teams. I was very impressed with the younger teams today. They've really moved forward and had a lot of progress.
And I was going to say that this is going to have me go back on Monday morning and talk to our engineering folks and say they better get busy and get to work because there's people ready to take their jobs coming down the pike.
That's right.
That's the hope. That's the goal here.
So just like last year, the next steps will be that each of your teams will be receiving a stipend to help you build out your prototypes or refine your prototypes if some of you have already built them already. And then you will be testing in a growth phase for the end of phase 2. So the final submission for phase 2 will basically be the results of your plant growth inside of your system. So we're really excited to see what comes out of this phase 2. And we're hoping that you all can spread the word. If you know other teams that were submitting, we're giving this extra 2-week chance so that we have other finalists joining on you and get even more ideas to NASA about automating their plant growth in the International Space Station and beyond. So thank you again for joining us today and for presenting. And you'll be receiving further instructions via emails.
Congratulations, everyone. Great work.
Thanks, everybody.
Yep, thank you for your time.
Thank you as well.
Thanks for the opportunity, everybody. Take care.
Thank you.